Hello, everyone. I'm Dima Faour-Klingbeil, the principal consultant and business owner of DFK for Safe Food Environment. I provide training and consultancy services in food safety management system and compliance audit to food industries nationwide and international. I'm very delighted to join my colleagues in this symposium to discuss a key topic to food security, which rely a lot on water. My presentation is on regulating water reuse in food production and food processing. It could be broader, this topic, than what I would cover. Therefore, I would look so much forward to your questions, to our discussions, and to exchange views on how water reuse could be promoted while protecting consumer health. So I would start my presentation with a brief overview on the crisis of water scarcity, which has been ranked as the top global risk in the world according to the Economic Forum report. So water scarcity problem is not an issue that is confined to a region, to a country, or to an area. It's affecting everyone, all of us, although in varying levels and degrees, depends on the country conditions and environment and practices. The implication could be quite impactful socially, economically, politically, and on the health and the nutrition of the people. So 2/3 of the people in the world, which is around 4 billion, are living in areas which has a severe water scarcity. And 500 million, they do experience limited access to water almost all the year round. So that problem and its magnitude could be enormous from one country, while probably it's less for another, due to several factors. And there are different factors that contribute to the water scarcity, and that would be described in the next slide. Sorry, yeah. So as shown in this water stress map, the water scarcity is spreading across the globe. The colors of red and light orange and dark orange, these are all signifying the countries that are actually approaching water demands that exceed the water availability. So it is particularly the problem concentrated in the Middle East and North African region, and in the arid region at the Mediterranean. And that is here estimated in these areas that the countries might face absolute water scarcity in 2025, and that could be before any all other countries. But Europe, although it has plenty of water resources, it actually also it's facing for the last decades a growing problem related to water stress, and that is particularly due to the water scarcity, but also to the deterioration of the water quality. So the figures indicate that there is almost 81% of fresh water is being withdrawn and extracted for agricultural use, potable use, but also for the industry. And the industry is the major abstractor of water in Europe. So there is no one factor that actually contributes to water scarcity. The one of the major contributors is the population growth, and that is estimated to continue growing to 9.5 billion in 2050. So with this continuous growth, there is an increased demand for water, there is an increased demand for food, and of course this would go hand in hand with the consumption pattern that's changing in some societies which are relatively economically relaxed, and there is a wide option of different foods like processed food, ready to eat, ready to cook food. It matches the fast-paced lifestyle in these societies. That in turn actually drives the industry to intensify its production, and that would be not the case sometimes in other parts of the world where other problems contribute to water availability or diminishing water availability, and that's water pollution that limit people to access fresh water and clean water, and the wasteful use of water and exploitation of groundwater resources, particularly in countries where the water policy and underground water management is deficient or poorly implemented. So all these together would actually become worse when it comes to the climate change. It is estimated that the global demand for water, in that case, due to climate change that exacerbate the problem, would rise by 55%. And more facts and figures in this slide, it specifically shows that with the continuous and constant growth and demand of and the rising demands for food and water, there is an estimation that the food production would increase by 60% over the same period when the estimated population growth is estimated to increase to 9.3 billion in 2050. But at the same time, also there is a projection that the industries, manufacturing industries, will have a demand for water that would increase by 400%. So that also indicates there is the growth in energy demand that is also water intensive and expected to rise as well by 50%. The food and agriculture sector are also a major contributor to water withdrawal. They are the major consumers for water. We can see, however, a different pattern in Europe. While it could range between 70 to 80% for the water withdrawal, it is much more the other way around. It's the reverse trend in Europe, where the industry is the major abstractor of water. And this clear disparity in industry-specific needs between the different countries is also reflected in the way they respond to the ongoing challenges of water scarcity. And with the increased water uses, the wastewater generation and discharge is also increasing in volume. And that can actually has implications and impactful implication on the environment and the ecosystem. So in the recent years, we have seen that there is a rise, and that's the rise in transition to reuse water, and the awareness in the industry is increasing on the importance of reducing waste and recycling, recovering the resources. So on one hand, that is mainly to minimize the cost of wastewater discharge or control the cost of wastewater discharge, but also to ensure that there is a constant supply of water, particularly in the countries where there is a climate change effect related to the frequent drought. So such transition from the linear model of economy to a circular approach entails that there is a shift from the take, make, consume, and dispose model to a circular economy, which is based on reusing the water as much as possible, conserving these vital resources. So by this, there is a minimization of extracting resources by closing the loop. And that transition has been seen with the European Commission that has put forward in 2018 the proposal for a regulation on the minimum requirement for reused water. In 2020, the regulation has been officially published on the minimum requirement for water reuse, and it reinforced that commitment towards promoting water reuse for irrigation and for agricultural needs through setting minimum regulatory requirement for water reuse in its Annex 1. The Annex 1 in the Regulation 2020 specifically laid down those requirements that are applicable to reclaimed water that are intended for use in the agriculture or for agricultural irrigation. Therefore, adequate treatment within the context of promoting circular economy should be reinforced for the water to ensure that it meets the drinking water standard when it's safe to be used in food production, and that particularly when it comes to direct contact with food or food contact surfaces. So supplying the water that is necessary in terms of its quality for reuse is a great challenge for the food industry because of the microbiological risk that could be associated with the water that would be reused, but also because of the well-established regulation in this regard. For instance, the conventional wastewater treatment would usually end with the secondary treatment, and that is not efficient to remove all the different compounds or the different pathogens that would render the water safe for reuse. That would need a further advanced treatment in order to eliminate and remove any potential microbial pathogens or nutrients through advanced processes. And that would actually serve the purpose for using it directly in irrigation or for any other purposes or industrial use. So in the food industry, water is used in throughout the production and different steps. At the primary production stages, the main user of water is the irrigation, for instance, the post-harvest washing, the sorting. It's also directly used as an ingredient in food formulation. It's used as a conveyor to transport food materials through the process, washing, rinsing, blanching, cooling, and other functions indirectly as well. It's used for cleaning and sanitation, the production equipments between operation. So there is an extensive volume of water that's used in the food industry. And the cost of that water supply and the volume discharged is actually the driving force for the industry to rethink and start adopting the sustainable production, considering reuse as a vital source for water. So that is also the case for the agriculture, particularly in the areas where reuse water is also very important due to the diminishing availability and accessibility to fresh resources. And that's particularly the case in many developing countries that are also falling under the water scarcity problems. So in terms of the water reuse as a definition, since that would be mostly and repetitively mentioned in my presentation, the water reuse definition, according to the EPA or the Environment Protection Agency, is reclaims water for, or it means reclaims water from a variety of sources, then treats and reuses water for beneficial purposes such as agriculture and irrigation, potable water supplies, groundwater replenishment, industrial processes, and environmental restoration. So that actually falls within the same context of Codex Committee on Food Hygiene that defines water use as any water that has been recovered from a processing step. And that includes water from the food components, and that after reconditioning treatment is intended to be used in the same prior or subsequent food processing operation. So that means water reuse includes reclaimed, recycled, recirculated, and reconditioned water as per definition. So along the farm to fork, there are several steps and several stages. And in this presentation, we want to discuss the primary or the primary production stage, and that's on farm. The water reuse suitability on farm or in the processing industry all under different consideration because they're dictated by the quality of water that is required for a particular operation or for a particular purpose, and by the quality of the water that has been generated, and that's what is needed to be used or to be treated for reuse. And at the same time, it's dictated by the type and the level of treatment. So it's important to know the basic quality or requirement of the water quality to be used in each step of the processes or of the process that can be used without affecting the finished products and harming the consumer. That's quite challenging in the absence of clear guidelines or criteria, because this requirement would vary depending on the production conditions, depending on the type of food production, and also the countries. For instance, on farm, the contaminants in terms of types and concentration level in wastewater, which will be reused for irrigation, for instance, or other functions like post-harvest, would vary greatly in its profile when it would actually be compared to the food processing, particularly the microbiological profile that could contain a wide spectrum of pathogens that are of fecal origin. And that include as well chemical contaminants that has a different profile than what we might have in the food processing industries. On farm, the contaminants are greatly affected by the environmental condition, the human activities. So we can see there are wide variation in countries. So for example, in some countries where the wastewater use and irrigation is regulated by water quality requirements and crop restrictions, that might not be the same in certain region where to overcome the water shortage and due to inaccessibility to fresh water, there is a spread and widespread use of wastewater that is untreated or inadequately treated, and that would introduce a lot of risk, industrial effluents that could be in some countries mixed with the domestic wastewater, and that would put a burden on the capacity of the wastewater treatment plants, but also would constitute a major health concern when it comes to persistent chemicals in the water that would enter the food chain, such as pharmaceuticals, antibiotic residues, and dioxins, and others. In comparison to on farm, the food processing water effluents have different characteristics from the microbiological profile, but also a complex mixture of constituents, and these could take into account for any recycling and reuse. For instance, the water in food processing are characterized by having a high BOD concentration or high biochemical oxygen demands and high level of other dissolved and suspended solids such as fats and oils and grease, and nutrients related to phosphorus or chemicals that be contained because of the sanitizers and the detergents that are used. So whatever the water reuse or recycling options to be chosen, it must be in line with the legal requirements and should satisfy the quality and the safety criteria. Under the current legislation, and that is the Drinking Water Directive, it is clear that the processed water that is used in the food industry should be at least equal to the high standard for drinking water as required by the local authorities. So the water used in the food processing that would come into direct contact with food or as an ingredient has to be equivalent to the potable quality standards. As for the agriculture irrigation, we refer again to an example of the European regulation, to the 2020 regulation, where there is a clear emphasis that reclaimed water used in agricultural irrigation should be safe for its intended use in accordance with the directive as well, 91. And this is further elaborated in the regulation when it comes to the classification of food and the quality parameters that are required. We can see this in the next slide. The European guidelines lay out the minimum requirement for the reclaimed water quality according to the classes of food. So for instance, class 1, food consumed raw, would have a certain minimum requirement for E. coli, and that comes with the permitted use and the irrigation method for each of the class. And class B is the food that's consumed raw without skin. It has also its corresponding regulatory requirement. So this is quite a strict approach when it comes to enforcing water quality parameters. They can be stricter for some other nations. So there are wide variation among the reuse scheme and regulation on the level of treatment required between countries. If we can look at the USA, EPA guidelines, the food crops that are eaten raw and not processed, it's required that the water quality should not contain coliform and should be monitored and tested daily. So while these are strict guidelines and strict approach, other guidelines are based on more flexible approach by initially defining the health target, which represent the acceptable risk of infection. And that depends, of course, on the required level of safety from the local context. So once the health target is defined, the quantitative microbial risk assessment model would be applied or used. And this is where the input assumptions would have to be defined. For example, the volume or the consumption volume. In this example here, in this slide, this is an example for the water supplies. So the model input would take into consideration the consumption volume, the dose response relationships for the reference pathogen, the exposure frequency, and that is to be estimated. For instance, we assume that this is a daily exposure for the entire year. And then the model will generate the annual risk infection in terms of disability adjusted life year. So, and that outcome will indicate if the treatment, operation, and controls are sufficient enough to meet the legal requirements which are set according to the health target. Otherwise, when not, the optimization of the treatment will have to take place in order to establish a water quality that meets the tolerance risk target determined by the regulators. So this risk-based approach has been as well adopted by different countries. And for example, the Dutch Drinking Water Act, which requires as well the implementation of risk assessment for waterborne pathogens. So at every water supply, to demonstrate that the safe water is in line with the legal requirements and is in line with the health-based target of less than 1 infection per 10,000 per year. So beside that, the producers would rely on the quality indicators that would have to meet the requirement of the absence of E. coli or enterococci. The health target is included in the legislation, and all the groundwater recharge systems or filtration systems have to demonstrate by applying quantitative microbial risk assessment that the water that is generated is actually in compliance with the maximum target level that has been established according to the Dutch regulation. Similarly, Australian has also implemented or based their guidelines on the risk-based approach to regulate the recreational water safety. So the QMRA approach is also used and integrated in the development of the water safety plans and the sanitation safety plans for the safe reuse of wastewater for irrigation. And this has been promoted by the WHO in their guidance and guidelines as a preventive risk management and a multi-barrier approach for both the non-potable water and also for the potable water reuse scheme. So to reduce the risk of pathogens across the entire water supply from catchment to consumer. So this plan is based on the same principle of the hazard analysis and critical control point, where there is a team responsible to identify the hazards, evaluate the associated risk in terms of the severity of the hazard and what is the likelihood of the occurrence of microbiological, chemical, or other hazard. And that's followed by determining as well the correct control measure to at the same time determine whether existing control measures are sufficient or they would require additional measure. The validation of control measures would have been established to define the quality parameters in order to monitor the process and verify that it is effective in meeting the health-based target. So whenever there is a loss of control or deviation, there are corrective actions or there is a clear procedure to craft the necessary solution in order to optimize the system and modify all the given parameters and treatment efficiency. In the stages of the primary production of food, regulation are largely based on quality parameters for water and restrictions or crop restrictions basis. In the food processing industry, the current regulations, whether the European regulations or the US FSMA preventive rule, but also others in Australia and Canada, they all emphasize and they generally agree on the importance of ensuring that the water used in food processing must be of a quality that's safe and suitable for human consumption. And that's particularly in the US, water that comes into direct contact with food. It's clearly defined in the regulation that has to be of adequate sanitary quality, and that is equivalent, it means, to the potable quality standard. Similarly, the Codex Alimentarius, Australian, New Zealand food standard codes, and many others do refer to potable water as the default quality or water quality in the food processing. So only potable water should be used in food handling and processing as published in the Faour recommendation, a general principle of food hygiene. At the same time, regulations are increasingly promoting or advocating water reuse. And that also we can see not only in the regulation, but also in the Faour recommendation that made it possible using water quality other than potable quality, provided that the competent authorities are satisfied with the wholesomeness of the foodstuff not affected. So we can see also that with the with the statement extracted from the Committee on Food Hygiene of the Codex Alimentarius Commission, which published the draft guidelines on the hygienic reuse of processing water in food plant. And that states that while water should be reconditioned to a level safe and suitable for its intended use, reconditioning to the level of potable water is unnecessary in many cases. However, reuse of water for incorporation into food products shall meet at least the microbiological and chemical specification of potable food. So with these current regulations and recommendation that made it possible to reuse water or water qualities that is not potable, provided that the industry would present or demonstrate to competent authorities that the water is safe for the finished product, it becomes obvious the importance of implementing an assessment or conducting an assessment of the microbiological, chemical, and physical hazard that could enter the potable water when it would be first used in the food processing operation, and to determine the degree of treatment or reconditioning required for its reuse for the next step or the second food processing operation. So basically, any reuse of water should be for the safety of the finished product, subjected to a hazard analysis. So the documentation of the HACCP, it becomes important in this case, where in the way that they will help the food manufacturer to provide the evidence and the documentation for the competent authorities when it comes to the safe reuse of water. There are several challenges for promoting water reuse, and they could differ in their nature as well, depends on where the water is applied and reused. For instance, at the primary production stage, there are health concerns related to pathogens and to emerging contaminants, pharmaceuticals, antibiotic residues in water, and these could actually be great in areas where there is a kind of haphazard use of wastewater and for irrigation. The limited data availability and input to conduct a proper and adequate risk assessment or QMRA are also posing a challenge for promoting water reuse and for reassuring the safety of the water to be reused for food production. For example, data on pathogen level and type of contaminants in the water after the first use is very important to be identified and thoroughly identified in order to devise the adequate treatment and control measures. And sometimes the pathogen persistence or behavior under different processing environment is also limited. Poor access to urban sanitation has also been cited as one of the major challenge in water reuse, because that could lead to cross-contamination of water pipe, and that seems to be reportedly common. So information on the pipeline system is important when implementing a risk-based system designed to focus on high-risk areas. It is assumed that food facility can access this information and would have a robust program where there is a hygienic design to the water conveyor system and pipelines. A significant cost is another challenge, because this could limit accessibility to to adequate technology, but also to staff who are skillful to establish systems that are based on risk assessment and to select the proper water quality parameters and conduct risk assessment in a manner that is based on the current scientific understanding. The lack of common standard of water reuse would add another obstacle on the movement of food product across borders when irrigated with reclaimed water. So to overcome these challenges, the regulatory framework to support water reuse is essential. And the question is harmonization by setting a minimum requirement for water quality capable to address the potential risks that are specific to different processing and production environments? How would that minimum requirement tackle these differences? So with this question, I thank you for attending the presentation and the symposium, and I look forward for the discussions and your insights. Thank you very much. And with this question, I would end up my presentation, and thank you for listening, and looking forward to the end of the symposium for more discussion and insight into the topic. Thank you very much.